Hi everyone, this session is on decimation in time and decimation in frequency. What is the meaning of decimation? Decimation, as per dictionary, it is destruction of a bigger group into smaller pieces. So we are now going to look at decimation in time and decimation in frequency. The outline of this presentation is going to be like this. Introduction to fast Fourier transform, which is the abbreviation of FFT. Next followed by decimation in time, DIT. And decimation in frequency is abbreviated as DIF. The differences and similarities between this DIT and DIF, this is what we are going to see in the outline of this presentation. So the first one is, what is Fourier transform? A Fourier transform is a useful analytical tool that is important for many fields of application in the digital signal processing. In describing the properties of the Fourier transform and inverse Fourier transform, it is quite convenient to use the concept of time and frequency. In image processing applications, it plays a critical role. Fast Fourier transform was first proposed by Cooley and Tukey in 1965. This fast Fourier transform is a highly efficient procedure for computing the discrete Fourier transform, that is DFT, of a finite series, and it requires lesser number of computations than that of a direct evaluation of DFT. So that is actually the main aim of fast Fourier transform. This FFT is based on decomposition and breaking the transform into smaller transforms and combining them to get the total transform. So this is what I told you. As per the meaning, we are now going to decompose a bigger sequence into smaller sequence, and we are going to apply the transforms. After doing all the processing, we are going to combine them to get the total transform. Yes. So this is discrete Fourier transform. Hope you are all familiar with what is discrete Fourier transform. The transform which helps us to convert this time domain to frequency domain. Now you will have a question in your mind. What is this time domain? What is this frequency domain? Time domain is an information represented by a signal can be obtained at any instance of time. That is, the signal information can be obtained at any instance of time. That is time domain. But we are not able to calculate the rate at which the information is varying, the rate at which the signal is varying. So in order to calculate the rate at which the signal is varying, we are moving on to the frequency transformation. Probably the previous topics of this unit will give you a better explanation of why people have transformed from time domain to frequency domain. Now ultimately, coming to our topic, the main aim of discrete Fourier transform is to convert a time domain sequence into a frequency domain sequence, right? So what is the formula for DFT? X of k, this is actually the frequency domain output. X of k is equal to the summation of n is equal to 0 to n minus 1 x of n into e to the power of minus j 2 pi by capital N k into kn. So where n is the total number of sequence, and smaller n takes the values from 0 to n minus 1, right? So how can I calculate the inverse? Is there a possibility to convert frequency domain to time domain? Yes, it is possible using discrete Fourier transform. We call that as inverse transform. So while applying inverse, we are supposed to get x of n, right? That is what we gave in the previous case. So x of n is equal to 1 divided by n. the summation of k is equal to 0 to n minus 1, because the parameter that we have used for a frequency domain here is k. So summation of k is equal to 0 to n minus 1 x of capital K. Here we have used minus j. Instead you use a plus j. E to the power of j 2 pi by capital N into Kn. So these two are called as Fourier transform pairs, because we can convert a time domain signal into frequency domain signal as and vice versa as well. So this is actually the baseline for, this is actually the Fourier transform pairs explanation, right? What is the baseline for computational complexity? What is mean by complexity? See, more the number of operations, your operation or the computational speed or the rate becomes complicated, right? So in DFT, each DFT coefficient requires, so how many number of computations are carried out when I am using this DFT? So DFT carries out n complex multiplications and n minus number of complex additions. So this is the case for DFT. So it is executing n complex multiplications and n minus 1 complex addition. So this is the case for a coefficient. Now what will be the case for all n DFT coefficients? How many computations we require? It requires n squared complex multiplications and n into n minus 1 complex additions. Do remember this, don't forget. N squared complex multiplications and n into n minus 1 complex additions. Yeah. Now, what is the necessity for this fast Fourier transform? Ma'am, you have told already time domain sequence has to be converted to frequency domain, and there is no issues, and we were able to convert it using a discrete Fourier transform. Then what is this FFT? Yes, this fast Fourier transform is an algorithm used to compute the DFT. Already time domain sequence has been converted to frequency domain and vice versa as well. Now this fast Fourier transform is an algorithm used to reduce the number of computations that have been occupied or that have been used for DFT calculations. So how is it possible? It is making use of the symmetry and periodicity properties of twiddle factor. Twiddle factor is Wn. So this is actually a coefficient. It is a trigonometric constant coefficient which can be multiplied by all the various operations that we require for the processing to effectively reduce the DFT computation time. So ultimately, what is the aim? We are trying to reduce the n squared complex multiplications and n into n minus 1 complex additions, right? So it is based on the, how come it is possible? It is based on the fundamental principle of decomposing the computation of DFT of a sequence of length n into successively smaller DFT. So this can be obtained only by decomposing the structure into smaller DFTs. So how is it possible? Yes. So we already, as said already, it is done by using symmetry and periodicity. So what is symmetry? Wn. What is this Wn? Wn is a factor called e to the power of minus j 2 pi divided by capital N. N is the total number of sequences, total number of discrete inputs present in the sequence, capital N. Wn to the power of kn star is equal to Wn to the power of minus kn. Probably you would have gone through this properties already. What is periodicity? Periodicity is Wn to the power of kn is equal to Wn to the power of k of n plus capital N. So even after the sequence is added with the n number of samples, it will remain the same. It will give us the same sequence. That is periodicity. So which can also be written as Wn to the power of k plus capital N into n. So this is also possible by using periodicity. One more possibility is Wn to the power of minus kn is equal to Wn to the power of k of capital N minus n, which is equal to Wn to the power of small n into n minus k. So these are the properties of periodicity. Similarly, there are some other twiddle factor parameters also which is satisfying the periodicity properties, like Wn to the power of nk can be written as it is equal to n to the power of nk multiplied by m on both the scripts. Capital N to the power of nk can be written as Wn to the power of small nk by m, that is divided by m on both the superscript and subscript. Wn to the power of n by 2. I told you already what is W suffix capital N. W suffix capital N can be represented as e to the power of minus j 2 pi by n. E to the power of minus j 2 pi by n. So 2 pi by n into n by 2, because we have capital N by 2 in the superscript. So while multiplying that, n and n will get cancelled, 2 and 2 will get cancelled, we will get e to the power of minus j pi. What is e to the power of minus j pi? What is the trigonometric representation? We can write it as cos pi minus j sin pi. Am I right? So what is cos pi? Cos pi is minus 1, sin pi is 0. So the twiddle factor of Wn to the power of n by 2 can be written as minus 1. Wn to the power of k plus n by 2, in a similar way of calculation, do remember Wn takes the value e to the power of minus j 2 pi divided by capital N. So substitute in that, you get minus Wn to the power of k. So this is how we calculate the periodicity, and we are using these two as the key properties to reduce the number of computations in DFT, which forms our fast Fourier transform. Yes. So the fast Fourier transform algorithm provides speed increase factors when compared with the direct computation of the DFT of approximately let's say 64 and 205 for a 256 point and 1024 point transforms respectively. So it is drastically reducing the number of computations required. So the number of multiplications and additions required to compute an n-point DFT using radix2 algorithm FFT are it can be calculated by using the formula capital N log to the base 2n and n by 2 log to the base 2n respectively. So this is the number of multiplications and this is the number of complex additions that is taken by this FFT, which reduces the numbers very drastically. Yes, so the example for the reduction in the multiplication and addition using this FFT and direct computation is given as follows. The number of complex multiplications required using direct computation is n squared is equal to 64 square, which is equal to 4096. The number of complex multiplications required using FFT is, so that this is actually calculated for a n equal to 64 point DFT. So when FFT is considered for the same n equal to 64 point, so how much is the number of complex multiplications getting reduced? See, it is actually 192, a very lesser value. You can look at the speed improvement factor, which is equal to 4096 divided by 192, which is marvelous, right? So 21.33. So these many number of computations are reduced, which means the speed is increased. So what are FFT algorithms? Do we have any algorithms to perform this computations? Yes. Basically, it is classified into two types. One is decimation in time and the other one is decimation in frequency. First, we are going to look at what is decimation in time algorithm. So, decimation in time algorithm. So, a key hint I am going to give you. In time, time is what is the parameter that we are using for representing time in DFT? N, smaller n represents the time domain. K represents the frequency domain. So if n is getting decimated, we call it as decimation in time. If k is getting decimated, we call that algorithm as decimation in frequency. So in DIT algorithm, DIT algorithm is used to calculate the DFT of an n-point sequence. The idea here is to break the n-point sequence. As I told you, decimation is breaking a larger sequence into smaller sequence. So capital N-point sequence is broken into two sequences where the length of the sequence will now become n/2 point sequences. How are we going to split? So that is actually the major part. So now in DIT, we are going to split the sequences into even sequence and odd sequence. That is represented as smaller xe of n. E represents even and O x naught of n. O represents odd numbers. So yeah, the sequence is now split into even and now there are two n/2 DFTs formed. N/2 DFTs of these two sequences are evaluated and combined together to give the 2-point DFT. Similarly, this n/2 point DFTs can be expressed as a combination of, once again there can be a split up, right? So once again I can divide it into n/4 point DFTs. Ultimate aim is you can divide it into smaller groups and reach towards the smallest group. Once again combine it back to form the n-point sequence. So this process is continued until we are left with the 2-point DFT, because we are going to propose a structure for radix 2-point DFT. Right. So this algorithm is actually called as decimation in time because, as I told you already, x of n is often split into smaller sequences. So how can I decide, on what basis we can decide the length or number of decimations that it has to perform? So there are different radixes we have in algorithm. It starts from radix 2, radix 3 and radix 4. Now in our syllabus we are going to see only radix 2 algorithm. So radix 2, as told already, the length of the sequence is capital N and we are representing an integer called as L. So capital N is equal to the length of the sequence is represented as 2 to the power of L, where L should be an integer value. So to decompose an n-point time domain signal into capital N signals, each containing a single point, each decomposing stage uses an interlace decomposition separating the even and odd indexed samples. To calculate the capital N frequency spectra corresponding to these capital N time domain signals. So this is a diagrammatic representation of how the split up is going to look like. So this diagram actually says a 16-point DFT. So if I'm having 16-point signals, how can it be split? As I told you already, DIT has to be split into even and odd sequences. So while splitting, you are taking out the even numbers and odd numbers separately. So this will become two 8-point signals. And once again, if you are splitting, as told already or as mentioned already, we have to go till 2-point sequence. So once again split up. So in all these cases you can see it is only even and odd. So this side it is even and this side it is odd. So we are splitting it till it becomes one point sequence. One point sequence is actually with the diagram which we are going to use in general is a 2-point DFT. So this is actually the starting point of the FFT calculation. So this is how it is looking like. Yes. What is the algorithm? Probably this algorithm will be explained you in a detailed manner and by another video. Now I am just going to brief you what are the steps that we are using in radix 2 DIT FFT algorithm. So ultimate aim is to divide the sequence into two. That too in DIT it is going to get divided into even and odd sequences, right? And I told you already n is going to get divided, n is going to get decimated, right? So when you are saying that it has to be split into even and odd sequence, how can I split it into even and odd sequence? It can be 2n. See, look at this, 2n on 2n plus 1. You should remember that any number of variables in the place of n can be used, but whichever is the variable used, it is representing only the time domain variable n. So here we are, in order to avoid the confusion, we have taken r. R is nothing but the same n. So what are the possibilities? It can be an even value or an odd value, is it not? So when we are saying it is an even value, x of 2r, which is nothing but the same x of 2n. Do remember that r is your n. Whereas for getting odd values, x2 of r is equal to x of 2r plus 1, 2n plus 1. Well, what is the value of r? R takes the value, it is half, right? So r is equal to 0 to n by 2 minus 1. Whereas what is the value of n actually for DFT? It is 0 to n minus 1, 0 to capital N minus 1. So how are we going to calculate this? We already know the formula for DFT. For obtaining x1 of k, use the DFT formula. So now the limits are r is equal to 0 to n by 2 minus 1, x1 of r into wn by 2 to the power of rk. Similarly, write it for x2 of k. Whereas we know already x1 of r is an even sequence, x of 2r, and x2 of r is an even odd sequence, x of 2r plus 1. So replacing that, now what is the value of k? There are two different variables, right? One is r and the other one is k. K you should write till the end of the algorithm. So k takes the, when n takes the value 0 to n by 2 minus 1, k will also take the same value 0 to n by 2 minus 1, right? So this is even and odd split up. About a sequence which is in the half portion. So the next half can be calculated by using the periodicity property. So x of k plus n by 2 can be represented as x1 of k plus n by 2, the same sequence in the next half. Wn to the power of k plus n by 2 into x2 of k plus n by 2. Right. So Wn to the power of k is a constant which can be written. Wn to the power of n by 2 we already saw in that previous slide, right? I already told you Wn takes the value e to the power of minus j 2 pi by n. Minus j 2 pi by n, in that n by 2 gets cancelled, we will get e to the power of minus j pi, which is cos pi minus j sin pi. Cos pi is equal to minus 1. So this minus 1 is actually carried out and it is placed here. So this is actually obtained because of the periodicity property. So now it takes the value k equal to 0, 1, n by 2 minus 1. Yes. So now what has happened till now? X of n has been split into two sequences, x1 of r and x2 of r, which can be taken as even and odd, and that was transformed as x1 of k and x2 of k. Ultimately, at last what are we doing? We are combining both to get the same x of k. So this is actually called as decimation. We are going to draw the same and represent the same by using an easiest structure, which is the magic of FFT, by using a flow graph called as butterfly structure or butterfly flow graph. X of k is equal to x1 of k plus wn to the power of k x2 of k. So these two are for the lengths, half lengths, right? So x of k plus n by 2 is the next half of the equation. Now how can we draw a 2-point DFT sequence? Let's say the two inputs are x1 of k, x2 of k. When I am drawing, see, it has to be a cross line like this. This arrow mark represents it is multiplied by a unit value. So draw the node points so that you are not deviating from it. So the arrow representation is like this. Follow my pointer path. So it is going like this. And for this input, it goes like this and this. So for computation, the input goes directly like this and a split input goes like this. Here this operation is direct, goes like this, and this operation is like this. And here in this line it is multiplied by -1. Why is it getting multiplied by -1? You can look at this. There is a -1 present in the transformation. So we are multiplying it by -1. What is the twiddle factor that we are going to multiply? Wn to the power of k. So what is the output of this sequence? This is actually combining both complex multiplication and additions. So how is it happening? Let us see. So this variable directly goes first, which is x1 of k, right? The next variable comes like this. The next one is x2 of k, which is multiplied by the twiddle factor wn to the power of k, and it is multiplied by once again 1. I told you already this arrow mark represents unit signal. So multiply it simply by 1. What do you get? x1 of k plus wn to the power of x2 of k, right? Similarly, look at the output at the other point. So first one is once again and again you bring the first variable first. So what is the first variable? x1 of k. So x1 of k comes directly. There is no other factor here. So it is simply multiplied by 1. It is x1 of k minus, why do we get minus? First, listen here. So this input has to go as the next parameter, right? So x2 of k multiplied by wn to the power of k, and then it is multiplied by -1. That is how you get this variable, or you get this parameter x1 of k minus wn to the power of k x2 of k. So this is how it has to be followed. Multiplied the input parameter with the twiddle factor first and then multiply it by -1. So this is how we are computing the 2-point DFT sequence in an FFT. So how many number of multiplications and complex additions are there in a 2-point? There is only one complex multiplication and 2 complex additions in a 2-point DFT. So this is how it is proportionately increasing for the number of points. So this is actually a block diagram representation of an n-point DFT. Now I'll tell you why do we or how is it actually divided into an even sequence and an odd sequence. So we have already seen it has been divided into x1 of r into x2 of r. This is your even sequence. What are the even numbers we have? 0, 2, 4, 6. Odd numbers 1, 3, 5, 7. So these two are, see, this is now split into two n by 2 point DFTs, right? So n length has been split up into 2 n by 2 point DFTs. So this 4 combines an even sequence, then this 4 combines the odd sequence, right? So when this is going to the output, we get all the 8 outputs. before going to the outputs, it has to be multiplied by the twiddle factors. So what are the twiddle factors that we have to multiply? As seen already, it has to be multiplied by Wn to the power of k. As seen already, all second lines has to be multiplied by the twiddle factor Wn to the power of k. Now here k takes the value 0, 1, 2, 3 because k ranges from 0 to n by 2 minus 1, right? So it takes the values 0, 1, 2 and 3. We are multiplying it by the twiddle factors. Consider all this n by 2 point as second line. So all these lines has to be multiplied by minus 1. See, look at the second 4 lines. You consider this first 4 lines as a single line in a DFT, 2-point DFT, whereas the second set of 4 lines has the second line in the 2-point DFT. So all these lines has to be multiplied by minus 1. Yes. So this is a flowchart representation. How we can synthesize or how combine DFT in radix 2 radix 2 DIT FFT. So first step is we are combining two 2-point DFTs into 4 segments like this, and for this 2-point and this 2-point are combined together to form a 4-point DFT, that is synthesize the 2-point DFTs into a 4-point DFT. This is becoming an odd even sequence and this is an odd sequence, and all these 8 inputs to form a synthesize to form the 4-point DFTs into an 8-pointer. So this 4 points will make a 8-point DFT. So how many stages of synthesizes or how many stages of decomposition are there for an 8-point DFT? You can look at the capital N is equal to 2 to the power of 3, where 3 is an integer, a L value. 2 to the power of 3 is 2 into 2 into 2, it is 8. So n equal to 8 can be synthesized by 3 stages of decimation. So that is what is shown in this picture. So at the end of this computation flow graph, at any stage, the output variables can be stored in the same registers previously occupied by the corresponding input variables. So this is actually the most special point that has to be described in an FFT, which is called as in-place computation. In-place computation in the sense, we took 2 variables, right, x1 of k and x2 of k in a 2-point DFT. So that 2 variables were calculated into 2 different outputs. What are those 2 different outputs? x1 of k plus wn to the power of k into x2 of k, and x1 of k minus wn to the power of k into x2 of k. So these 2 were the outputs, right? As soon as these 2 outputs are calculated, we don't require the 2 inputs, right? x1 of k and x2 of k are no more required. So the output values which are calculated can be stored in the same memory location as stored earlier. That is what this sentence says. Now just I'm reading the sentence once again, just follow me. At the end of the computation flow graph, at any stage, so on any stage, the output variables can be stored in the same register previously occupied by the corresponding input variable. So if I am filling the outputs that are obtained in each stage in the previous input location, this is actually called as in-place computation, and this in-place computation is actually at memory location sharing. So this is how it is reducing the significant requirements of memory that is occupied in DFT. So in-place computation, you should never forget in-place computation. So the distance between the two nodes in a butterfly structure, that is n equal to 2 to the power of L. There are L stages. So how many stages we have? Depending upon the L value. So if it is 1, it is 1. The stage 2 is 2. That is L value is 2. It is 2. It is 3. The number of distance is 4, and L is equal to 2 to the power of L minus 1. So these are the distance between the nodes. Right. How to calculate this? Ma'am, when it comes to a problem, how can we consider this? How can we consider this bit reversal, or how can we consider this even and odd sequences? Now we are going to follow an order called as bit reversed order. In the DFT computation scheme, the DFT samples x of k appears at the output in a sequential order, while the input samples x of n appear in a different order called bit reversed order. So what is this bit reversed order? Now look at this picture. Probably this will give you a clear explanation. I told you DIT is decimation in time. That is, n is going to be split into even and odd sequences. Is it not? So let's say m is actually the sequential binary form and n is the bit reversed form. Look at this. Normally for n equal to 8 point, we know what are the binary forms we need. What are the binary combinations possible? It starts from 0, 0, 0, 0, 0, 1, 2, 3 up to 7 we have 1, 1, 1. Now reverse the entire sequences independently. So 0, 0, 0. The next one is 1, 0, 0. Reverse the sequence. So what will you get? After reversing, look at the sequence. It is 0, 4. I am telling you the decimal equivalence. It is 0, 4, 2, 6, 1, 5, 3, 7. So these are the representation of binary forms, which we are popularly calling it as bit reversed order. So the input in the DIT radix 2 algorithm is in bit reversed order, whereas the output that we are going to get, that is x of k, will be in normal order. So how is it actually getting decimated? This is actually an evidence for your input bit reversed sequence. So there are 3 binary values, n2, n1, n0. How is it actually split? 0 and 1, and this 0 and 1, 0 can be split into 0 and 1. This can be split into 0 and 1. Now look at the sequence. So this can be written as 0, 0, 0. This is 1, 0, 0. Then next one is 0, 1, 0. The next one is 1, 1, 0. This is looking back. Just look at the back. And the next one is 0, 0, 1. The next 1, 0, 1. Next one is 0, 1, 1. The last one is 1, 1, 1. So this is how we are forming the bit reversed sequence, as we did earlier. This is one more method of representation. So make it for sure in your mind that in DIT, the input is in bit reversed order. Yeah. So that's it for DIT algorithm. The next comes is your decimation infrequency algorithm. So it is as simple as possible. We are going to now, as I told you already, frequency is the parameter that we are going to decimate here is k. Now it is a popular form of FFT algorithm. In this, the output sequence x of k is divided into smaller and smaller subsequences. That is why the name decimation in frequency. So this is what I told. K is going to get divided smaller and smaller. Initially, the input sequence x of n is divided into 2 sequences, x1 of n and x2 of n. First consisting of n by 2 samples of x of n, and the last consists of n by 2 samples of x of n. Respectively. So have a very simple note. It is going to split it into 2 halves. So whatever is the endpoint algorithm given to you, whatever is the endpoint sequence given to you, you split it into halves. That is 0 to n by 2 minus 1 will be the first half of the sequence, and n by 2 to n minus 1 will be the second half of the sequence. That is no even and odd sort of thing. It is simply half sequences divided. So that is what we are trying to say. The former n by 2 point is x of n, and later n by 2 point is x of n plus n by 2. There we saw n getting decimated. Here we are going to look at k getting decimated. So this is how the structure looks like. If I am taking an n equal to 8 point sequence, so it is divided into two halves. 0, 1, 2, 3 will form the first n by 2 point, and 4, 5, 6 will form the next n by 2 point. So look at the arrow marks. This is how the butterfly computation works. So this is taken now as a 4 point, and this is taken now as a 4 point. So once again, what will we do? We are going to split it into two halves. Same thing, n by 4, and this is n by 4. This is one n by 4, and this is one n by 4. So finally, the same thing comes to 1 point. So what happens here is, the input is now taken. What is the case in DIT? The input is taken in bit reversed order. The output was in normal order. Is it not? Output was in normal order. Probably I missed the pointer. Now I am showing it once again. So this is 0 to 7, that is n equal to 8. So this is split into two halves, and this is now split into two halves. So the last sequence is in bit reversed order. So here the input sequence is in normal order, output sequence is in bit reversed order. So this is actually the vice versa thing that we are going to follow while calculating the problems. Except for this is the most important expected 16-mark question of this unit, and this is very easy, in fact, if you follow the very simple procedure. Yes, so this is a gist of the algorithm, where algorithm will be coming in a different video. So x of k can now be x of k. This is actually the actual formula for DFT. X of k is equal to the summation of n equal to 0 to n minus 1, x of n into wn to the power of nk, which is equal to, now I told you it is divided into two halves. So first half is 0 to n by 2 minus 1. The next half is n by 2 to n minus 1. So if this is the case, how will be the symmetry and periodicity working? So this first half, I can change it to the same limits. So in order to bring it to the same limits, this is also one same half, right? So I can simply change this limits also as 0 to n by 2 minus 1, because the length of the sequence is the same. So while making this, what I am supposed to do here, in order to bring n equal to 0, I should add wherever n is there in this, the smaller n has to be added by n by 2. So that is what we are doing. See, n plus n by 2, n plus n by 2. Once again, calculate the periodicity property. As told already, it is becoming minus 1 to the power of k. K equal to 0 to n minus 1. So this is how k is getting decimated. So this is just showing you the first stage of decimation. Probably in the algorithm you will detailed look. So now this is actually the x of k sequence, which is split into two halves. Now we have to think, while getting decimated, it is obviously going to get divided into odd and even sequence, right? So in that x of k, what is the even sequence, what is the odd sequence? So now you should be very careful in looking at the algorithm. There n got decimated, here k is getting decimated. So now here this 2r represents the value of k. Look at this. There I told you n is taking the value 2r and 2r plus 1. Here we have to be very careful. It is k taking the value 2r and 2r plus 1. Right? So the same thing. Instead of k we are using 2r, and instead of k we are using 2r plus 1. So two different sequences. Apply that in the formula we'll get the we have to work on the algorithm and we'll get the sequencer. So this is actually the 2-point sequence. So this is the butterfly structure that we are going to use for DIF calculation. What are the two different inputs here? X of n and x of n plus n by 2. Now how see, look at the node points, look at the diagram. There we had a twiddle factor before the second variable, before it is getting multiplied by -1, whereas the operation is totally different here. Look at the sequence. So again same 4 node points in order to draw it neatly, and then drop the arrows. Once again this input has to go one input directly, one input this way. Once again this input, one input directly, and the other input has to go in this way. This arrow represent multiplied by 1. That's it. Now what is the output? X1 of n and x2 of n are supposed to be my outputs, let's say. In that case, what is getting added? So the first input goes directly so into 1 x of n. Hope you understand. One more input is coming from this end. That is next variable x of n plus n by 2. So x of n plus n by 2 into 1 comes to plus x of n plus n by 2. Similarly, look at the variable of x2 of n. How do we get this structure? This is actually the standard structure which has been framed already by Cooley and Tukey. So this is multiplied by -1. Here the twiddle factor is wn to the power of n. There in DIT we had wn to the power of k. So just note it very seriously. So now what is x2 of n? As usual, drop the first variable. X of n into 1 into wn to the power of n, right? Into wn to the power of n. So this becomes a common because it is going to be multiplied. The twiddle factor is a common variable for both the inputs x of n and x of n plus n by 2. So be careful in that. The next variable is x of n plus n by 2 into -1, the whole thing into wn of n, right? So this wn of n is common for both. So I am putting it in the outer and including this x of n minus x of n plus n by 2 in a square parenthesis, square bracket. So how many number of computations are required for calculating a DIF? 1 complex multiplication and 2 complex additions. So this is how the block diagram looks. I told you already, it is the input has to be taken in the normal order. The output has to be taken in the bit reversed order, but this is not the exact output. It is actually the first stage when it is converting it into n by 2 point, second stage output is shown here, n by 2 point DFT and n by 2 point DFT. So here the twiddle factors are, in DIT what we used to do, the twiddle factors were multiplied before getting into this butterfly, whereas here the butterfly only after the butterfly structure is over we are multiplying it by the twiddle factors. Once again the value of n is taking the value 0, 1, 2, 3. So this is the only difference between your DIT and DIF. So this is actually showing you a butterfly which is fluttering its wings, right? So contracting and relaxing its wings. So this is actually a sample diagram which we are going to look in the tutorials. You can now look at. So this diagram you have to be there in your memory. Even during sleep you should remember this. If you are remembering this, then for sure 16 marks is there in your hand. Never forget it. So in DIF for n is equal to 8 pointer. How many 8 pointers? 2 to the power of 3. How many stages? L is the number of stages, as I told you already. So L is first stage, second stage and third stage. So the input sequence is divided into two halves, right? So input is in normal order, output is in bit reversed order. So first stage is like this. Always do consider, have your 2-point structure in the mind. First parameter with the input goes directly. Second parameter will be multiplied by, second line will be multiplied by -1. So all the second set of lines will be multiplied by -1. In DIT, we used to have a twiddle factor multiplied before, whereas here we have a twiddle factor multiplied afterwards. Right? So this is how it is split, and this is a 2-point DFT. And finally, the output order we are obtaining is in bit reversed order, but this is not actually the correct output. After getting the bit reversed order, we are supposed to write what is the value of x of k. While writing x of k, you have to bring it to normal order and write. Only that will be giving the correct sequence of data. Ma'am, till now you were explaining about DIT and DIF. Whether you are telling about the same n equal to 8 point. Will it give the same answer for while I'm doing it in DIT and DIF? Yes, it is going to give you the same answer. Either you do it in DIT or DIF. So both are having the same output. So both will, in both the different algorithms, while you are processing, you will get the same output for the DFT sequence. So what is the comparison between DIT and DIF? The order of the samples. DIT FFT, the input is bit reversed order and the output is natural order. DIF, the input is in normal order, natural order, and output is in bit reversed order. Regarding the butterfly computation, DIT will have multiplication done before addition, whereas DIF will have multiplication done after addition. So these are the comparison points between DIT and DIF. So both DIT and DIF FFT have the identical computational complexity because they share the same number of decimations, that is capital N is equal to 2 to the power of L. There are L stages and each has n by 2 butterfly computation. Each butterfly computation has 1. Right? So both DIT and DIF have the characteristics of in-place computation. So that is the most important point. In-place computation. In-place computation is, do remember, I take two input variables, do the signal processing using the radix to DIT, the radix algorithm, apply the algorithm and get the processed outputs. Now the processed outputs no more require the input from which it has been calculated. So we can store these outputs at any point of time in the decimation. All these outputs can be stored in the same memory location previously stored by the input parameters. So this is called as in-place computation. A DIT flow graph can be transposed to a DIF FFT flow graph and vice versa. So thank you for this. Thank you for patiently listening this presentation. Thank you.